Alright, let's make sure we got our notes out here for this video. We're going to go over some terminology in regular polygons and talk about some properties of regular polygons. And then in the next video, I'll show you how we construct regular polygons by compass, straight edge, and with GeoGebra. Okay, so make sure your notes are out, please. Alright, before we talk about regular polygons, we need to define first of all what a polygon is. Whenever you hear this word, first of all, roots. It's good to know roots of words because if you know what it means, you can define a lot of other words. Poly, by the way, means many, and gon means side. These are Greek roots. Poly, like polytheistic or polygamy, means many, right? Many gods, many wives, whatever. Polygon means many sides, so a shape with many sides. So what a polygon is a closed plane figure that has straight sides. Those sides are just line segments. Okay? So here's a picture here of some polygons, not polygons, and then how we can also categorize polygons by their shape. But what closed means, if you look at the polygons here, closed means that the shape doesn't have any gaps or holes in it, right? It's just an enclosed shape here. If you're a little ant walking this, you could just walk the whole path with no gaps or anything. Okay? Whereas in this not polygon, look at this shape here. This is not a polygon. This X is not a polygon because it's not closed, right? A line segment is not a polygon because it's not closed. There's no connecting. Polygon has to have three or more sides to make a closed shape, right? If you had a two-sided shape, it'd just be like an angle, wouldn't it? Like a segment coming off of here. Let's see, maybe like this. So if we took this segment here, oh, green's probably not a good color for this. So just change this color, maybe make it red. So you can see this two-sided shape, right? It looks just like an angle, but that's not closed. So to close a shape, you have to have a minimum of three sides, right? If I took my other line segment tool there, sorry, it's green again, but I hope you can see that the closed shape, which makes a triangle. The triangle is the most basic polygon, right? It has three sides. And then we can classify polygons by two ways, really. We got concave, convex, and we also have by the number of sides, right? So triangle, tri means three, quad means four, so we have a quadrilateral. Deca, from like a decade, means 10 years, right? Decade means 10 years, so deca means 10 sides. So we got a decagon, and that's how we classify polygons, by their name, by the number of sides, right? The other way is concave, convex. The difference between these two, just like this picture shows, concave to me means cave. When I think of cave, I think like a cave-in. So a side got caved in here, right? Like this Pac-Man mouth, this one, this little mountain-looking thing here. It's like if you took this vertex that's kind of caved in and you popped it out, it would be a triangle again, wouldn't it? Which would be a convex shape. So concave means a side of a convex shape looks like it got caved in to make that shape. That's how I think of it, at least. Convex means it's kind of what I consider like a blown out shape, right? All the sides are out. Okay? So that's the difference between concave and convex, and we also classify polygons by the number of sides, and we name them that way. Okay, so now that we know about polygons here, we're on the same page there with polygons. Let's talk about regular polygons, which is a convex polygon with congruent sides and angles. So notice all of these shapes here are regular polygons, and all the sides are the same in length, so they're congruent. So in a geometric diagram, we would just make sure that we show that. We would have to show the congruent segments on all of these, right? So just so you know, this guarantees that it's regular, but because it tells us it's regular, because we know that it is, we can assume that they're all the same, and we don't need to show these congruent marks. But if I just gave you a triangle, we don't know that anything's congruent in them unless we denote it with our notation. So, alright. Man, there's a cat. Sorry, I hope you can't hear that cat meowing. Anyways, so make sure that you have a list of the polygons named, please. On the quest, there's a hyperlink. Please click on that. Go to a nice website that has a list of the names and shapes. Write that down in your notes as well. But here's an example of regular polygon in nature. We got honey honeycomb here. These are just regular hexagons, right? And then we have a stop sign, which is considered a regular octagon. Okay? So when we think about regular polygons, we talk about especially how do we construct these polygons. We want to think about symmetry, because especially how to construct, we're going to use symmetrical properties, whether it's what we consider rotational symmetry or what we consider line symmetry. Line symmetry would just be reflections, right? Rotational symmetry would be like this hexagon here. I have a little dot that could be like the center of the polygon. If it was the true center of this hexagon here, then we could rotate, say like this corner, some angle measure, right, to map onto this corner. And then if we did that, so just to show the angle here, if we did that, like this angle right here, if we just rotated this whole polygon, whatever this angle measure is, not only would this point map onto here, but because of symmetry, this point would go to here, this 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 would go to here, right? Which implies all these segments have the same length. Okay, so what we can see then is this symmetrical, I hope, symmetrical rotational symmetry that goes on in all of these regular polygons. And with even-sided shapes like a hexagon, 6 sides, true for a 4-side, 8-side, 10-side, when we draw these lines like this, notice this line goes from vertex to vertex, but in an odd-sided shape, like a pentagon, for example, if I drew from a vertex down, notice it goes right through the middle of a side. So in an odd-sided polygon, like a triangle, it's going to be the same thing. Nonagon means 9 sides, but still, if I go from a vertex to the opposite direction, it goes right through the middle. It doesn't go through vertex to vertex. Does in even-sided shapes, but not in odd. But still, we have symmetry. Okay? So we got nice symmetry going on in regular polygons. And now I just want to go over some terms with you with regular polygons so that we can talk about these later. Alright, so here's a regular polygon that I have for you here. Okay, we've already talked center of the polygon. Okay, so the center would be somewhere in the middle. And I'm going to show you how we can easily just construct the center. Notice in all these shapes here, if you were to think about rotational symmetry of this pentagon, that center point would be somewhere on that red line, right? Somewhere like right there. So we know that the center of a shape should be on that line of reflection, right? It should make sense, I hope, by now. So what that means is to find our center point, then all I'm going to do is just draw in some lines of reflection. So I'm going to grab my segment tool here, and I'm going to draw a line of reflection, maybe this vertical one here. Go right through the middle. Okay, there's a line of reflection there, line of symmetry. So that center point has to be somewhere on here, but I don't know exactly where. So I'm just going to do that again. Grab another vertex, go through the opposite midpoint. That would be the line of symmetry. And now we know the center has to be on both lines of symmetry, don't we? So that center point then would be right here, right at that intersection. So we just actually constructed, without guessing where the center is, we just use symmetry concepts to find our center. So now that I have the center of my polygon, I'm going to go ahead and just delete these lines of reflection that I used. So now I have my center, okay? Now radius of a polygon, or for plural, radii, radius is a word that we reserve with circles. So how do those relate to regular polygons? Well, if I make a circle centered at the same center of the polygon, so like right here, and I make a radius that goes out to a vertex. Notice every vertex is going out to that circle as well. Therefore, the radii of the circle are really the radii of this regular polygon here. So if I were to draw the radii from center to point on the circle, which are the vertices of the polygon, right? That's another word we need to know. These corners here are called the vertices. If we drew all those radii in, we can see our rotational symmetry clearly now. I hope you can see that. These segments have to be the same length because of the radii of a circle that touches all these vertices, right? And then we have also sides. These would be the sides of our polygon. These would be a radius, right? All of these would be radius, or radii collectively. Okay, we have the center. All right, now the vertex, oh, sorry, we've also talked about all these little corners here are called vertices. So I'm going to get rid of that circle now. So these are just called the vertices. Radii just go out from the center to a vertex. Make sure you have that in your notes. Okay, and then the last thing to talk about is our vertex angle, or what we call rotation angle. The vertex angle is actually kind of tricky. I like to call this the vertex angle, which you'll refer to in geometry books as a rotation angle. And I'll show you why. Because we're going to construct these regular polygons using rotation. Okay, and that's why I ask you this question here. What is the measure of the rotation angle? So rotation angle would mean, what angle do we have to rotate this polygon so that it just maps back onto itself, right? So if I rotate this, maybe this angle measure, whatever that is, right? This angle right here, if I measure that, wouldn't this point then just rotate to this point right here? Or actually, the rotation just follows this circular path, right? This point would just rotate on this path and stop right here. This vertex would rotate on this path and stop here if we rotate that angle. That's what we call the angle of rotation, so, or rotation angle. So that's these angles in here. Okay. Now the reason it's also called a vertex angle, not to be confused with these vertices of the polygon. If you were to just kind of pull out one of these triangles, maybe I'll make it yellow here. So I'm just going to highlight one of these triangles. Okay, like this one. If we were to just look at it, not even look at the polygon, anything else around it, just look at that triangle itself, okay, then this is actually an isosceles triangle, right? Because these radii lengths right here are congruent, aren't they? Okay, so this is an isosceles triangle. So what we call the angles in an isosceles triangle, these are what we call base angles. And if you remember symmetry here, if I do that line of symmetry, then these angles have to be the same, don't they? If we were to fold this on that line, this angle would map onto this angle and they're going to be the same. So these are what we call base angles. This is really the base of an isosceles triangle. This is what's called the vertex angle. If we talk just isosceles triangles, this is what's called the vertex angle, which is also that angle of rotation. So that's why it's called the vertex angle as well. Okay, we'll take some formal notes on those terminologies later, but just so that you've heard it, we have a base, makes these base angles. Base angles are congruent in an isosceles triangle. Just keep symmetry in mind. And then we have what's called the vertex angle. Okay, so last question here is, what is this rotation angle in here? Okay, let's actually find the value. What would we have to rotate these points so that they would just map onto the next vertex? Okay, and here's how we can think of that. I'm just going to get my isosceles triangle stuff out of here. Okay, so now if you think about a full rotation, we need to know that if we rotated this point, say, along this rotation path here, that's really what this circle is, right? If we rotated this shape, it would rotate all around this, wouldn't it? Okay, so a full rotation, we know that if we went 360 degrees, this point would just map right back onto itself, right? A full rotation. Now, symmetry helps us know that all these rotation angles in here have to be the same, right? That's what symmetry is. So if those are all the same, how many angles are there? And notice there's one angle to each side. So we could either count the angles to know how many there are, or we can just count the number of sides, which will be the same number of angles. So this shape has 1, 2, 3, 4, 5, 6, 7. It's a regular heptagon. So to find that angle of rotation, all I have to do is take my full rotation. A full 360 would get me right back to where I started. And I'm going to take that full rotation and divide by how many equal angles there are. Wouldn't that just be what each one of these sevenths of the full rotation would be? So let me grab my calculator here. And let's find out what that is. And you guys need to have your calculator too. Not right now, but when you do these problems you will. I'm going to take 360, divide it by 7, and the rotation angle for this regular heptagon, and true for all regular heptagons. If we rotated this shape around the center, 51.42857,143. Don't really know what else is going on here, but close enough. If we rotate this angle, all these points would just rotate to the next vertex. Rotational symmetry. Okay, so that's how we find angles of rotation. So I hope those are good notes there for regular polygons.